In this in this video, we introduce quantum physics. Quantum physics is a branch of physics which is necessary to understand phenomena at very small scales, atomic, nuclear, subatomic. Since these phenomena take place at very small length scales, they're not directly observable in the macroscopic world. And many of the principles and results that we learn in quantum physics are very counterintuitive, very different from what we expect in the macroscopic world. It's similar in that respect to relativity, where also many of the outcomes were very counterintuitive. First of all, the word quantum, quantization. Things are said to be quantized if they can only take certain discrete values. So, for example, number of people in a room can only be an integer. It cannot be, 3.5 or 4 4/4. So we say that the number of people in a room is quantized. Similarly, number of electrons in an atom or electric charge we learned in the second semester is also quantized quantity because it only exists in multiples of the electronic charge. You can either have 1 electron, 2 electrons, 3 electrons, and so forth. In relativity, we learned that at speeds which are much smaller than speed of light, the equations of relativity go back to what they were in classical physics. And a similar idea is valid in quantum physics as well, and this is known as correspondence principle. So if you have large, slow-moving objects, instead of atomic, subatomic particles, if you have large objects which are moving at non-relativistic speeds, then quantum physics, the results of quantum physics, become identical to those of classical physics. And that's called correspondence principle. In the first section, let's begin with quantization of energy. In classical physics, we didn't have the idea of quantization of energy. You could have 1 joule of energy or 1.1 joules of energy or 1.1115 joules of energy. So there's no limit on how small changes in energy could be. However, when you get to the atomic scale, the energy of systems is quantized. It can only have certain discrete values. For example, if the kinetic energy of a car was quantized, what that would mean is you could only drive at certain discrete speeds only. 50 kilometers per hour, 55 miles per hour, 56, 57, but nothing in between. So that's basically what quantization would translate to. Quantization of energy of certain systems was the first phenomenon that led to the discovery of quantum physics. Before we get to quantization of this system, let's talk about the system itself, and that system is called Blackbody. A blackbody is basically a surface that can fully absorb all incident electromagnetic radiation. So any electromagnetic radiation of any frequency falling on an object, if that can be fully absorbed by the object, then that's called a blackbody. So a blackbody will not reflect anything or will not transmit any electromagnetic radiation inside it. All of it is completely absorbed. Now, all objects at a given temperature emit some amount of electromagnetic radiation. So what happens is, due to the thermal motion of the molecules that make up a substance, there's always a vigorous oscillation taking place, just like molecules of a gas are constantly moving around. Similarly, molecules of any substance, not just gas, are also constantly moving around because they have a certain finite temperature. I mean, the motion may not be as vigorous as it is for gases, but even in solids and liquids, you have that motion. Now, atoms, you will recall, are basically made up of positive and negative charges. And so moving atoms, moving molecules constitute electric charges that are constantly moving and accelerating and decelerating as they collide with other similar particles. So during this collision, there's an acceleration of the charged particle, which we know can create electromagnetic radiation. So some of the thermal energy, which is basically kinetic energy of these molecules, is being converted into electromagnetic energy, and that's emitted as electromagnetic radiation. So any object at a certain temperature emits electromagnetic energy. A black body does this with perfect efficiency. So there's no loss of energy when a black body emits electromagnetic radiation. The idea that this efficiency is perfect is expressed in terms of a quantity known as emissivity. So we say that the emissivity of a black body is exactly 1. Emissivity is represented by the Greek letter epsilon, and all real life objects have an emissivity which is less than 1, so they're less than 100% efficient. And yet their radiation can approximate black body radiation. Let me pull up the graph of black body radiation. So in this graph, what you see is the spectrum of black body radiation. On the y-axis, you have electromagnetic radiation, the intensity of electromagnetic radiation. And on the x-axis, you have the wavelength of the emitted radiation. So in between, the colored bands that you see are the visible part of the electromagnetic spectrum, but obviously black, as you can see in this graph, black body radiation exists in regions, in pretty much the entire region of the electromagnetic spectrum, both above the visible spectrum and below the visible spectrum. What you see in this graph are 3 different graphs at 3 different temperatures. At 3000 Kelvin, you have this flattish graph. And then at 4000 Kelvin, as you increase the temperature, it acquires a more prominent peak. Moreover, the peak of the 4000 Kelvin graph is a little bit to the left of the peak for the 3000 Kelvin graph. And then if you further increase the temperature to 6000, the peak becomes more prominent, and it has also shifted further to the left. Just a word about these specific temperatures. 6000 Kelvin, an object at 6000 Kelvin is said to be white hot because it emits all possible radiation. At 3000 Kelvin, objects are said to be red hot because they have a glow which is reddish in color. And that has to do with the location of the peak that you see there. The peak is closer to the red end of the visible spectrum, and therefore what you see is a red glow. So for example, if you look at a stove in your kitchen, when it glows, you see this red color. So that's because of the temperature and the peak being close to the red end of the visible spectrum. It doesn't mean that the other frequencies, other wavelengths don't exist, but it's just that that's the most prominent one. So at room temperature, most of the energy that is emitted in the form of blackbody radiation is in the infrared region. However, as the temperature increases, lambda max decreases, which is what I was pointing out earlier. Lambda max is the wavelength at which you have maximum intensity. So that's what's shown by these peaks. The wavelength at which you have maximum intensity at 3000 Kelvin is somewhere around here, a little less than 1000 nanometer. And then if you increase that temperature to 4000 Kelvin, as you can see, lambda max, the wavelength at which you have maximum intensity, is now smaller than that. And then at 6000 for white hot objects, it's even smaller. So as temperature increases, lambda max decreases. The intensity of the light that's emitted, the intensity of the radiation that's emitted, is directly proportional to the fourth power of the temperature in Kelvin. So if you double the temperature, the intensity would increase 16 times. Wien's displacement law gives us the dependence between lambda max and the temperature. It basically says that the product of lambda max and temperature is a constant. That constant is represented by b, lowercase b, and has a value of about 2.898 times 10 to the negative 3 meter Kelvin. Now, the relevance of blackbody radiation in this context is the following. If you look at the exact shape of these curves, classical physics was unable to describe why these curves of blackbody radiation should have this particular shape. So this was a puzzle for physicists for a long time, like why exactly does that have this characteristic shape? Among many physicists who were working on this, Max Planck, a German physicist, he came up with this model of atoms and molecules, whereby these atoms and molecules are seen as oscillators, as tiny objects that are constantly oscillating, which is not very far-fetched because we know that atoms and molecules in a solid at a finite temperature are indeed oscillating, are vibrating. So Max Planck thought of atoms and molecules as oscillators that emit and absorb radiation. So if you add, or if you have incident radiation on an oscillator, it would absorb the energy. By the same token, it can also emit energy in the form of radiation. Now, in order to theoretically obtain the correct shape of blackbody radiation curves, Planck had to assume that the energies of these oscillators were quantized, meaning these energies could not have any random value. They have to have certain discrete values. And he deduced the energy of an oscillator of frequency f to be given by this equation. E equals n plus 1/2 times a constant h times the frequency f. N here in this equation is a non-negative integer, so 0, 1, 2, 3, etc. H is a constant called Planck's constant, which has a value of 6.626 times 10 to the negative 34 joules seconds. Now, when an oscillator emits or absorbs radiation, its energy can decrease or increase. If it absorbs radiation, its energy would increase, and if it emits radiation, its energy would decrease. But this change, increase or decreasing, can only occur in discrete steps of HF. So the energy of these oscillators can only change in steps of HF, 1 HF or 2 HF or 3 HF, but nothing in between. This is analogous to, if you remember, the standing waves experiment where from first semester, where you could have a one loop pattern of standing waves or two loop patterns of standing waves or three loop patterns, but nothing like 1.5 or 2.5. So this is similar to that. Now, this idea for energy to be quantized was something which was not familiar to physicists and was quite a radical idea. In fact, it was so radical that Planck himself had a hard time accepting the validity of quantization of energy, that energy could be quantized. Now, if you look at the value of Planck's constant h, it's so small, 10 to the negative 34. And that's the reason why we don't experience this quantization in the macroscopic world. You don't notice that energy can only have certain discrete values. So as far as we are concerned, energy is continuous. Objects, macroscopic objects, can have any value of energy. One system in which the quantization of energy is very starkly, very clearly seen is in what's called an atomic spectrum. So when atoms absorb energy, their own energy increases. When atoms absorb electromagnetic radiation, their energy increases. But they can remain at this higher energy level only for a period of time, and then subsequently they fall back to the original value of their energy. In doing that, when they fall back to the original value of energy, they emit back the radiation that they had absorbed, or they emit back the energy that they had absorbed. And that energy can be seen if it's in the visible part of the spectrum. You can see that. It is found that each type of atom has its own characteristic discrete spectrum of wavelengths that it absorbs and re-emits. So these atoms cannot absorb and emit any random wavelength. Each atom has its own specific wavelengths that it can absorb or re-emit. And this suggests that the atomic energies must be quantized as well. Let's look at the electromagnetic radiation spectrum of oxygen. So this is the spectrum of oxygen that you see here. And as you can see, it's these lines that you find in pretty much the entire spectrum. So there's a red line here. There are two green lines and so forth. So as you can see, it's very discrete. There only is like certain values. It's not a continuous glow, but you see these sharp lines of high intensity light. So this is the emission spectrum of oxygen. So if you have an oxygen atom and it absorbs certain amount of electromagnetic radiation, and then it re-emits it after a while, this is the light that comes out of oxygen. So basically the idea here is that the energy spectrum of oxygen and all other atoms as well is quantized. They only have discrete wavelengths. And because of the characteristic nature of this discrete energy, the energy spectrum or atomic spectrum, this can be seen as a signature of a specific atom. So if you're given a spectrum of this kind, you should be able to figure out what is the atom involved here, because each atom has its own specific signature spectrum. So observation of atomic spectra help us identify elements. Um, for example, if you look at sunlight and look at these atomic spectra in sunlight, you are able to identify the elements that exist in the outer core of the sun. There's an interesting example of the element helium. Helium actually turns out was discovered first on the sun rather than on Earth. So scientists were studying the radiation from the sun, and they noticed certain lines which they could not match with any of the known atoms. So for that reason, a hypothesis was proposed that there must be an element in the atmosphere of the sun which doesn't exist on Earth. And this element was given the name of helium. Helios is the name for sun. So helium from there. And subsequently, after the hypothesis of existence of helium on the sun, subsequently helium was also discovered on Earth as well. Okay, we'll continue with photoelectric effect as one of the quantum phenomena that is foundational to quantum physics in the next video.